Why is the tension drawn away from this link?
Oh,
It's fixed on the wall, but tension is always drawn away from the body. So if we draw this guy, we have to draw the tension this way. But he's pulling me too, so if we draw a free body diagram of me, it's pulled that way. Tension always goes away from the body that you're analyzing. So in this case, I'm analyzing the link. TA is drawn away, TC is drawn away. When I analyze 2, TA is drawn away here, TB is drawn away there. Right? Everybody got that? If I were to combine these two, and we don't need to in this problem, I just want you to get used to combining things. So if I have link 1 here and link 2 here, I would have to draw a TC, right? I would draw 500. I would draw a TB, and I would draw the weight. Right? How come I'm not drawing the tensions in here? They cancel out. From link 1, there's a TA going to the right. And from link 2, there's a TA going to the left. They cancel out. You could say they cancel out. Is that cable experiencing a tension?
Yeah.
Yeah, otherwise it would collapse, right? It is experiencing tension, but the forces that are in there, the tension in there is an internal force. So from this free body diagram, we wouldn't be able to calculate TA and TA at all, because it's internal to the system. It's not an unknown here. It's only when you put it here that you can actually calculate them. What's missing from this free body diagram? The axes. Gotta draw the axes. Gotta. What's missing from this free body diagram? The angles and the axes. And it doesn't matter where you put the axes, you get to decide, but you have to draw them.
Would we have to put TD in the second body?
No, you don't have to anymore.
Okay.
Because good question. We already reported that TD is equal to W, right? So you could box this in and say, done. We figured it out already.
Okay.
Now we just solve for W, and when we solve for W, whatever it turns out to be, once we box it in, and we box in that, the person who's reading it knows TD is equal to W. Okay. Raya.
The problem has newtons and you have pounds.
Oh, newtons?
Yeah.
Thank you. Sorry. Thanks. Okay, you ready to go on to another one? Okay, we're going to go to a 3D one now. Okay, Lonnie, we're up to you. Okay, what's the first thing we do? Okay, look at the picture, read the words. The block is supported by a system of cables. The weight of the block is 500. Find the tension in, here, Eric, we're answering your question already. So it's asking, okay, so is there anything that's given in the words that's not in the picture? What? The weight is 500 newtons, sorry. And I'm going to draw it here. This is my scrap, right? Okay, what do they want us to find? TA, TB, and TC. Do they care what this cable is? Is there a cable there? Does the cable have a load?
Yeah.
What is it?
Yeah.
W, 500 newtons, right? But I'm not going to draw it, I'm not going to put it in the table at all, because right now I'm saying this is W. So let's draw our table. Force, magnitude, direction. Okay, Chris, what are the forces present here?
We got weight,
The weight, magnitude, do we know?
500 newtons.
Yeah, direction?
Yeah.
Okay. Keep going. What else do we have? Chris?
I think that's it. Oh, well, we have TA, TB.
Right. So we put all the forces in the system. Do we know their magnitudes?
No,
No. Do we know their
no,
directions?
we don't.
Yes, because it's tension's always along the line of the cable, and it's always drawn away from the body I analyze. So I know the direction. They gave me all the distances.
You don't know them yet. You know the components to get the direction, but you don't actually know the direction.
Right, but you're gonna know it.
Right.
It's given.
Okay.
Okay, it's given. You're so deep. See, you're gonna show me some code.
Nope.
No. Okay, did everybody get that?
Yeah.
They gave us the direction, so we know it. Okay, we just have to calculate it. So, any other forces? Rachel? Okay, how many unknowns do we have? 3 unknowns. How many equations do we need?
3.
So how many bodies do we need to analyze? 3D.
Oh, 1, right.
One body, oops. One body. Because it's 3D. It's a 3D problem. So Sarah, what body do you want to analyze?
I'm going to analyze that body in the middle.
Okay, tell me what it looks like.
Round.
Like a lake, right? Like a lake? You mean this, right?
Round.
Why did you pick that point?
Because that's the center point where all the forces are concurrent.
Right, all the forces converge on that link, that's what we want to do. So when we draw this free body diagram, Daniel, if I draw the link, which direction am I drawing the tension in? Away, because it always gets drawn away from the body. How about B?
Outwards as well.
Outwards. How about next one? Same, and this last, and the weight?
Absolutely that way.
Down, weight. I'm not going to redraw it because it'll just take us a while to redraw it. But those of you, like I looked at all those little pieces of paper you gave me, was it Tuesday? And I sent you an email on the things that, summary of what people wanted help on, and today I'll be there in the STEM Center from 12:45 to 2, working on those things. But one was 3D. I would suggest those of you who are really, not that comfortable with 3D, draw this thing in 3D. And whenever I draw something in 3D, I always draw it using a box. So let's draw one. So first, 3D problem. Oh, somebody asked about axes. Look at the axes. So I'm going to draw this. Here's my x-axis. Here's my, y? And then here's my z. The axes are not always pointing in the same direction. Is everybody with me? Sometimes the XY plane is the horizontal on the ground, and the Z comes up because Z represents elevation of land. So many times you see it with the XY plane down flat. On the horizontal plane you see Z coming up. That's one way. Another way you see it is X and Y like this on the vertical plane, and what's sticking out at you? Z. X, Y, Z. So those are usually the two ways you see it. But the way you know is you look at the problem and you say, oh, okay, this is how they're doing it this time. X and Y are here. So we're starting at this point. For me, I like to put little things going that way so I can see. I'm going to do TA. So it's coming out 1.2. It's going up 2.4. And it's going in the Y a negative 1.5. Right? So we're going to draw a box. So here's my box. This line is parallel to the X. I'm going to do it light. This line is parallel to the X, and it's 1.2. This is parallel to the negative Y. Here's my Z coming up. 1.2 is here. This isn't that great. It's better with grid paper, right?
Yeah.
Yeah.
Read the grid paper.
So here's my box. Not too bad. So what was this, 1.4? 1.5. Here's my 1.2. So this line, 1.2, parallel, parallel. These are supposed to be parallel. This is up 2.4, 2.4, 2.4, and 1.5, 1.5. And then when I draw my force, I'm going from this point to which point? The top box, here or here? Let's check that. So am I still going positive 1.2? Going from here to here? Yes. Am I going negative 1.5 in the y? Yes. Am I going up 2.4? Yes. Okay. Now, those of you who took engineering 25, this is drawn, how did I draw that? As an oblique or an isometric? It's an isometric, right? But we could also draw it as an oblique. Oblique is when one side is perpendicular. Here's my box. And here's my, let's see where we want to put our origin. Probably right here. Here's my, here is, depends on how I'm going to look at it, I'm going to do this. This is going to be my y-axis. This is going to be my y. This is going to be my x. And here's my z. I wanted to come from the origin and I'm going which way? I'm going,
You gotta
Let's
move
go to the
your
negative
right.
y.
yeah, so let's see, if I'm going to, I'm going in a positive x, I'm going in a negative y, and a negative z, no, positive z.
Move your origin to the right.
Negative, which is negative, just y,
Yep. Yes.
so going from here to here, I'm going in the negative y,
It'd be the
No.
front corner, right?
Yeah.
Leave the Z or the Y
There,
there.
there you go.
positive x, negative y, positive z. Okay. Okay, let's go to another problem. We're gonna do a 2D. Everybody okay? So boxes, I mean, I'm on the spot when I'm up here doing it, but boxes are easier than just drawing all these lines. Sometimes it's kind of hard. But notice, 1.5, this line is parallel to the y-axis, so you know it's in y. 2.4, it's parallel to the z, so you know it's in the z. Okay, how about this? 2.1, where are we? Eugene, 2.1, what is that distance in? X, y, or z?
Why?
Why, how come?
It's going in the
It's going in the negative y, it's parallel to the y-axis, so you know it's a y distance. Okay, and I can help you, I can give you more practice on that. Okay, let's look at this one. Nick, yeah, Danny?
Do you want to see boxes on the graph, or could we, if you feel comfortable with just a line, is that all?
Yeah, you could do whatever you want, as long as it's clear. I saw somebody's homework though, where they went, they had the X, Y, no, X, Y, Z axis, and they went like this, F, and then they said 1.2, 1.5, 1.8. That doesn't help me, right? I guess this does give me information, but your graphical 3D view does not, it's not good at all. Yes, you are, and I just drew this, I guess I should have done it like this, right? It is giving me the directions of it, but does this F look 3D to you at all? It could be on a 2D plane. You have to show me graphically how this thing is 3D. Okay. Chelsea, masses of cylinder A and B are given. Determine the forces exerted on the cylinders by the inclined surface and magnitude. There's a lot of stuff in here, huh?
Yes.
Okay, given. What's given?
The masses of both cylinders,
So what do you want to call that?
A and B.
Okay, how about M sub A
Oh, yes. And so B.
and M sub B? Does everybody agree this is the notation you want to use? Okay? So whenever I'm given masses, the first thing I do, guess what I do? Convert them to weight. Because if I forget to convert them, I'm going to use 40 and 90 throughout the whole problem, and it's going to be all screwed up. So I'm going to go ahead and calculate. Weight of A is equal to MAG, and we're looking at, so it's 40 times 9.81. What does it turn out to be?